So we just finished talking about the end behavior or extreme behavior of a polynomial function, which tells us what's occurring on the graph at the ends or extremes of the graph. Now we'd like to find out what happens in the middle of the graph, the bumps, the peaks, and the valleys. And to find that, we're going to find all the zeros of the function. So remember that the zeros are equal to the value of x when f of x is equal to 0. Zeros are also known as x-intercepts or roots or solutions, depending on the situation or sometimes even the textbook. Also, I want to remind you that the number of zeros, now that's complex and real zeros, is equal to the degree. We won't be dealing with any complex zeros in this section, but we will a little bit later, and the number of all the total zeros equals the degree. Next, we'd like to talk a little bit about multiplicity. Multiplicity means how many times the associated factor for each of the zeros appears in the function. For example, a zero with multiplicity 1 means that the graph of the function crosses the x-axis at that point. An example would be a function that looks a little bit like this. It only has one zero or x-intercept, where f of x is equal to 0, right here. Notice it crosses right through. It doesn't have any more other zeros, but this is just an example of a multiplicity of 1. There's only one factor right here, or 1, 0. A zero with higher multiplicity can be broken up into two groups. A zero with even multiplicity, and then a zero with odd multiplicity that's greater than or equal to 3, meaning not 1, okay? Because 1 has its own properties. So a zero with even multiplicity, that graph of the function bounces or touches and turns around at the x-axis at that point. Mathematically, we call that tangent. And here's an example of that. Let's say I have a polynomial function. Right there at the x-axis, it has a 0, but it turns around. So on the first example, it went straight through. On the second example, it turned around. This would be an example of even multiplicity, where the 0 appeared twice in the factors of the polynomial. A 0 with odd multiplicity greater than or equal to 3, so odd multiplicity like multiplicity of 3, multiplicity of 5, not multiplicity of 1 because we've already talked about that case. In this case, the graph of the function also crosses the x-axis at that point, but with a wiggle. Or another way of saying that the graph is flatter at that point. So I might have a graph that does something like this, and right there at the x-axis as it crosses, it does like a little wiggle, or another way of thinking about it is that it's a little flatter right at that 0. So those are the three cases of what the graphs will look like. Let's talk about an example of each one of these so that it makes a little bit more sense. Each one of the examples, f of x equals x squared minus 4, x squared, or x cubed, we actually know what these graphs look like by using our transformations from a previous lesson. But I want to use that information to show you what the multiplicity would do here. In order to find the zeros, I'm going to set f of x equal to 0. I can factor, leaving me with x equals 2 or negative 2. So my zeros are 2 and negative 2. So I'll make a mark here and make a mark here, and that's going to represent negative 2 and 2. I know this isn't the best graph, but that's what we're going to do here. I also know that with an even degree, my leading coefficient, 1, is positive. So with a leading coefficient positive and a degree which is even, I know I'm going up and up. which makes sense because this is a quadratic. We know it's a quadratic x squared function, and minus 4 tells me that my vertex is going to be shifted down 4. So connecting these, I can create my quadratic. Notice that I have a 0 here. Just one copy of x minus 2 gets me a 0 of 2. One copy of x plus 2 gets me a 0 of negative 2. Just one copy of it. So we have a negative 2, 0, and notice the graph goes right through it. And we have a positive 2, 0, and the graph goes right through it. Because if you have a 0 with multiplicity 1, the graph just goes straight through the x-axis. Let's take a look at the second example. F of x equals x squared. Again, we already know what that looks like. Using our transformation and parent functions. My zeros, if I want to find them, I need to set f of x equal to 0. I could take the square root of both sides, and I get 0 equals x. So my 0 is 0. Although that I know that my number of zeros need to equal my degree, like we talked about earlier. And I only have 1 here. My degree here is 2, and that means I need to have 2 zeros. So what I want to do is I want you to think about it slightly different. Instead of taking the square root of both sides, so I'm going to erase this real quick. If I rewrote this as 0 equals x squared, and instead of taking the square root of both sides, what if I factored x squared? Well, the only way to factor x squared is just to break it up into its prime factorization, x times x. If I set each of these equal to 0, I get x equals 0, and then I set the other one equal to 0, I'm getting x equals 0. Notice that I have 2 zeros here. The number of zeros need to equal the degree, and that's including multiplicity. So I have a 0, and I also have another 0 of 0. Instead of writing 0, 0, which is a little redundant, what I want you to write instead is your zeros are going to be 0, multiplicity of 2. What happens at a multiplicity of even multiplicity? Well, right here at 0, notice my graph bounces or turns around. So instead of going straight through at the 0, it's turning around, which is exactly what we said in a 0 with even multiplicity should do. On the last example, we have f of x equals x cubed. Again, we already know what that looks like. We can already sketch this graph here because of our previous knowledge of this function. In order to find the zeros, I set f of x equal to 0. Again, I'm not going to take the cube root here. I'm going to factor it just like I did on the previous example. And if I factor this into its prime factorization, I have 3 factors. I'm going to set each of those factors equal to 0. I get x equals 0, x equals 0, and x equals 0. So the zeros or roots of the function is 0. Well, how many times over? Well, 3 times. So it has a multiplicity of 3. What happens at an odd multiplicity? Well, the graph crosses the x-axis, but with a little wiggle. And you can remember that because you know what the cubic function looks like. You know it already has a little wiggle there. The graph is just a little bit flatter before it takes off to go up towards infinity or down towards negative infinity. So that's what the 3 cases of the multiplicity is going to occur. Let's try a few examples putting the whole picture together and graphing our polynomial function. On this example, it says find the zeros of the following functions, then sketch the graph using the leading coefficient test. So my degree of this polynomial is the highest exponent, or 3. You can either put 3 or odd, I don't really care which one. The leading coefficient is 1, and you need to know that the leading coefficient is positive. With an odd degree, that means my arrow is going to be pointing in 2 different directions, and a positive leading coefficient, that's going to be down to the left and up to the right. And all you have to do is just put the arrows there, and that's good enough. Finding the zeros is probably the hardest part of this problem. In order to find the zeros, I'm going to set f of x equal to 0. And I'm getting 0 equals x cubed plus 3x squared minus x minus 3. The only way we know how to solve this now is to factor it. All of the problems in this section will factor quite nicely for you, or they'll already be factored for you. If the factoring is a little bit too hard, maybe an x to the 4th or an x to the 5th, we haven't quite covered that, but we will cover it, but just not in this lesson. We need to first learn about synthetic division. All of the problems in this section will be easily factored. So in order to factor a 4-term polynomial, I'm going to be using grouping. So I look at the first group and I say, what can factor out of x cubed and 3x squared? And the answer there is x squared. Out of the second group, what can factor out of negative x and negative 3? The answer there is negative 1. Are the two remaining binomials the same? Yes, they are. So I have x plus 3 as a factor and x squared minus 1 being a factor. And then I can finish this up by using a difference of two squares, x plus 1 and x minus 1. Set each of the factors equal to 0. I'm getting x is equal to negative 3, x is equal to negative 1, and x is equal to positive 1. Each of those factors appear only once in my polynomial. I have no duplications of my factors, so each one of these will have multiplicity of 1. If it has a multiplicity of 1, you don't have to state it. My zeros are just going to be negative 3, negative 1, and 1. And I can already put those 3 points on my graph. Because zeros are the values where f of x is equal to 0, they must also then be the x-intercepts. The only difference between zeros and x-intercepts are points, and so we're going to write them as such. So if you get zeros right, you better be getting x-intercepts also correct, because they're basically the same thing, just rewritten a little bit differently. The y-intercept is 0, comma some value, and the way we find that is to find f of 0. So I'm going to find f of 0 here, which gets me 0 cubed plus 3 times 0 squared minus 0 minus 3. I really like this part of the problem because 0 cubed is 0. 0 squared times 3 is 0. Minus 0 is 0. So really you're just getting that constant term. So I kind of like that. It's kind of nice. Alright, now I would like to use my end behavior and sketch the graph using the leading coefficient test. I know that my graph has to be smooth, no jagged edges, no sharp points, no holes. And I know that my end behavior has to go down to the left, yet up to the right. None of these zeros have multiplicity, so none of them will be bouncing like we had up here with an even multiplicity. None of them will go through with a wiggle with an odd multiplicity greater than or equal to 3. All of these just have a multiplicity of 1, meaning I'm just going to go straight through. At some point I need to turn around to come back to get negative 1. Do I know where this point turns around? Well, actually, I really don't at this point of our education. We will be able to find this. We just need to use a little bit of calculus, and we don't have that information. So if your graph goes a little higher than your neighbor's graph, that's probably okay. And then we're going to come back down and hit our y-intercepts. At some point we need to turn around and come back and hit our last x-intercept. Are we crossing all 3 of my zeros crossing through the x-axis? Yes. Have I hit my y-intercept? Yes. Have I used my end behavior to find the extremities of the graph? Yes, I have. This is a fairly good picture of the polynomial function. Again, it's not perfect. If I wanted to find a more perfect polynomial, I could pick some more points, but that's not what I'm asking you to do today. I'm asking you to find the zeros, the end behavior, the y-intercept, and draw a pretty good graph.